Welcome to this video on oscillatory motion part 3. In this video we're going to take a look at a spring oscillator rather than a pendulum oscillator like we did in the last video. So if you haven't checked that out, I recommend going back and checking those out. Again, I'm using a fet.colorado.edu simulator, and there's a link in the description below so you can play along. Alright, so what I have here is a 100-gram mass on the end of a spring that's attached to the ceiling here, and we're going to let it oscillate, and we're going to take a look at how each 2 pi radian cycle, how that will be affected by the physical parameters. So let's go ahead and do that. So I'm going to stretch this below the equilibrium position and release it, and there you can see I'm tracing out a period, which is a maximum amplitude on either side of the equilibrium. Now we could sit there and watch that for a long time, but let's go ahead and check this out. So we know here that in this case there is a restoring force acting on this object, but there's no restoring torque here because we don't have anything oscillating around some point. This is just up and down motion. We could also have the oscillator laying side to side. So we're going to say that this restoring force is equal to the spring force, or this force that the spring is exerting on this object, this mass. Now the reason that we can ignore the effect of the gravitational force on this object is because the gravitational force, whether the mass is above or below the equilibrium line, it's not restoring the mass back to its equilibrium position when it's moving in the opposite direction, whereas the restoring force of the spring is doing that. Now this is a linear spring, so the restoring force will always be directly proportional to the displacement, which means this is a simple harmonic oscillator. Now a simple harmonic oscillator, remember, is a linear relationship between the distance stretched and the force exerted at any given position. So let's take a look now and see if we could set up the function here. Now we know that 2 pi over t is the angular frequency for this motion. And we saw in the last video that the angular frequency is also some relationship of physical parameters, not only this abstract idea of 2 pi radians over t. So let's see what things affect the period of oscillation for this oscillating spring. So if I graph t versus, let's see, we already established that this gravitational pull is not really going to have much of an effect here because it's constant on both sides of the motion, and it's going to end up factoring out. So we'll leave that out. But let's take a look at the spring constant. Now that, remember, is how hard the spring pulls per unit of stretched distance. So we'll go ahead here and we'll watch this, and we can put a movable line in here so that we can establish kind of how high it's raising, maybe right to the center of the mass. Now if I increase the spring constant, what I see here is that it's moving a little bit faster, or maybe a lot faster. Let's see if we really exaggerate it. We see that this amplitude is maybe changing a little bit. The spring is definitely responding. And so as the spring constant increases, we see a definite increase in the period. Okay, and that makes sense because as it pulls harder, it will restore faster. The net acceleration will be greater. Now, if we were to actually graph these two, we know that as the constant increases, the period decreases, and we'll see again a relationship is t is proportional to the square root of 1 over k. Okay, and that looks familiar from the last one. Now let's see how the mass might affect this motion. So we'll go ahead and we'll lower the spring constant just so it's easier to watch. Turn off this movable line, and I'm going to increase the mass. it's very clear that it's definitely moving slower due to the greater mass. Alright, so what we see is definitely, or at least, a direct proportion. And if I were to graph the period versus the mass, what I'd see is a square root relationship again. So t here is going to be proportional to the square root of m. So again, if I put these two together, t is proportional to the square root of m over k. Again here, because we have the inverse, once we set 2 pi over t equal to the square root of this, which is the reciprocal, because t is in the denominator here, k over m, we see that once we solve for period, we get t is equal to 2 pi over root m over k. So we have a very similar relationship to the last situation. But what we're going to see now is, how is it that the angular frequency is the square root of two physical perspectives? So what we're going to do in the next video is take a look at setting up a differential equation that will be able to solve this situation. So what I want to leave you with here is write a net force equation for the situation, and then try to convert that net force equation into a differential equation. And we'll take a look at that in the next video.